Welcome to the chapter on vancomycin dosing and drug concentration predictions. Vancomycin continues to be an important antibiotic due to the development of resistance to other antibiotics, and pharmacists report that they participate in the monitoring and dosing of vancomycin quite frequently in hospitals around the country. The monitoring of vancomycin has changed over the years. In the 1980s, measurement of both peak and trough concentrations was common, whereas today the most common approach is to measure only a trough. Dosing adjustment with vancomycin tends to be straightforward based on measured concentrations because it generally appears to follow first-order elimination. Thus, changes in dose are expected to produce proportional changes in concentration. In this video, we will use estimated pharmacokinetic parameters to develop a dosing schedule designed to produce a desired trough concentration for a given dosage interval. I hope you enjoy the video.
Let's begin with our patient case. This is part 1 of the case. A 40-year-old male patient who weighs 120 kilograms with an ideal body weight of 80 kilograms has an estimated creatinine clearance of 75 milliliters per minute. He's going to be started on vancomycin for Staphylococcus septicemia, and doses are going to be given as 1-hour infusions. The target vancomycin steady-state trough concentration at your institution, measured 30 minutes before the next dose, is 15 milligrams per liter. We'll begin by estimating the patient's vancomycin clearance, elimination rate constant K, and volume of distribution in order to be able to predict the dose and interval. Let's start by determining the clearance of vancomycin. One of the equations found in the literature suggests that the clearance of vancomycin in milliliters per minute equals 0.689 times creatinine clearance, which is also in milliliters per minute, plus 3.66. Because our patient has a creatinine clearance of 75 milliliters per minute, we insert that into the equation and then do the solution and end up with a clearance of vancomycin estimated at 55.34 milliliters per minute. In order to convert milliliters per minute to liters per hour, we multiply the estimated vancomycin clearance of 55.34 milliliters per minute times 0.06. 0.06 comes from 60 minutes over 1 hour times 1 liter over 1,000 milliliters, which removes the milliliters and minutes and converts to liters per hour. And the final solution is our estimated clearance of vancomycin in liters per hour at 3.32. Next, we'll determine the volume of distribution. The volume in liters per kilo of vancomycin in adults is 0.62 of actual body weight, unless the weight is greater than or equal to 30% above ideal weight. That is, actual body weight over ideal body weight is greater than or equal to 1.3. Our patient weighs 120 kilograms, and their ideal weight is 80 kilograms. Thus, the ABW over IBW is 1.5, and they're considered obese. For obese adults, the volume is 0.56 liters per kilo, but still of actual body weight. Thus, the volume in this patient is 0.56 liters per kilo times 120 kilos equals 67.2 liters. Now we can move on and determine the elimination rate constant K. We know that K is equal to clearance divided by volume of distribution, and in our case the predicted clearance of vancomycin in this patient was 3.32 liters per hour divided by the predicted volume of 67.2 liters. This gives us a predicted K of 0.049 hours to the minus 1 and a corresponding half-life of approximately 14 hours. Let's move on to the second part of the patient case. Using the parameters that we predicted, let's now predict a dose to produce the desired trough of 15 milligrams per liter if doses are going to be given every 12 hours. When we want to predict the dose to produce the desired trough, we obviously have to use the equation that describes the method of dosing. And this is the equation, where the concentration at any time, capital T, after the end of the infusion can be determined. We have T prime, the infusion time, and tau as the dosage interval. Everything is known in this equation. Volume, K, we've determined that. We know the time of infusion. The only thing that we don't know is the dose. So let's refine that equation and put some numbers in. First of all, we decided that we wanted a trough of 15 milligrams per liter. That trough is going to occur 10.5 hours after the end of the 1 hour infusion, because the trough is going to occur a half an hour before the next dose. The 10.5 goes into the part of the equation for time after the end of the infusion. And then all we have left that's unknown is the dose. So let's move on to the calculation. Again, here's the equation with everything plugged in. The only thing that we don't have is D, or dose. If we solve everything on the right-hand side of the equation, it all comes out to be approximately 0.0195 multiplied times the dose. If we divide 0.195 into 15 milligrams per liter, it tells us that we need a dose of 768.1 milligrams, which will be given every 12 hours. And we would round that off to 750 milligrams or something close to that. Now, when we reduce the dose from 768.1 to 750, that obviously also changes our predicted trough concentration. We could go back in here and plug in 750 and solve for the concentration, or we can do it by ratio. I'm not going to do the calculations here, but just to say, with the reduction to 750 milligrams, the predicted trough is 14.6 milligrams per liter. For part 3 of the case, the patient is actually started on vancomycin at a dose of 750 milligrams every 12 hours. A measured steady-state trough concentration was reported as 12 milligrams per liter. Now remember, the predicted on 750 is 14.6, so our patient clearly has a faster clearance than that predicted from the population values. Suppose we wish to increase the dose to produce a trough of 15 milligrams per liter, since the patient isn't responding as well as we might desire. What we'll do now is determine the new dose to be given every 12 hours. In terms of the calculations, vancomycin follows first-order elimination processes. Thus, changes in dose produce proportional changes in concentration at the same time in the dosing interval. It's a critical factor if the dosing interval does not change. You can't use proportional dose change if you alter the interval, for example, from 12 hours to 24 hours. The simple way to do that is just by a ratio of, as you can see here, the new dose equaling the current dose times the concentration desired over the measured concentration. The values that we have are the current dose of 750 milligrams, the measured concentration of 12 milligrams per liter, the desired concentration of 15 milligrams per liter, and after we do those calculations, it says that our dose should be 937.5 milligrams. Now obviously that dose would be rounded to a logical value, such as 1,000 milligrams, which would also produce a slightly higher predicted trough. That difference can also be determined using the proportionality of the change. In this case, the new concentration is equal to the current concentration times the new dose over the current dose. So for example, the new concentration would be the current concentration of 15 milligrams per liter, which is predicted from the 937.5 milligrams, and the new dose of 1,000 milligrams, all together equaling 16 milligrams per liter. So if we used 1,000 milligrams every 12 hours, our predicted trough would be 16 milligrams per liter. And it's important to refine your calculations based on the dose that you actually use.